Hello, this is Professor Gutierrez, and we're going to be looking at section 5.3. Kind of doing webcam and a lecture at the same time, so you get to see me. It's going to be great. All right, in this section we're going to introduce Poisson distributions. All right, another category of discrete, not continuous, probability distributions. The z-scores will be a continuous probability distribution. All right. All right, so what a Poisson probability distribution is a discrete probability distribution that applies to occurrences of some event over a specific interval. The random variable x is the number of occurrences of the event in an interval. The interval can be time, distance, area, volume, or some other unit. It is given by this god-awful equation here. Probability of an event occurring x times over interval is given by p of x is equal to mu to the x power e to the minus mu over x factorial. You might want a calculator if you're going to calculate this one. I'm going to write that down. P of x. That did not work well. Oh, there we go. P of x equals mu to the x power e to the minus mu over x factorial. How about that? Now e, see this e right there? That's a number. It's 2.71828. You also probably have a button on your calculator that says e to the, so you can use that one when you're using that one. There's no mu to the x though. That's kind of sad. All right, so requirements for a Poisson probability distribution. Maybe me over here makes more sense. All right, random variable x is the number of occurrences in some interval. The occurrences must be random, makes sense. The occurrences must be independent of each other, perfect. The occurrences must be uniformly distributed over the interval being used. Great! Almost great. The only thing we really have is mu. So the mean is mu. Mu equals mu. Okay, that's an easy one. Standard deviation is the square root of mu. And of course the variance would be mu, because it's simply standard deviation squared. Properties of Poisson distribution. Determined only by the mean mu, because we only have the mean mu in the equation. You can take a look at the equation, mu to the mu to the mu. And, and it is only determined by the mean. Yep. So Poisson distribution has a possibility of x values of 0, 1, 2, 3, no upper limit. It could have a jillion. But a jillion is not a number, so not a jillion. All right. Example, Atlantic hurricanes, 1 of 5. So we had 5, no, we don't have 5 hurricanes. That's page 1 of, never mind. For a 55-year period since 1960, there were 336 Atlanta hurricanes. Assume a Poisson distribution. Find mu, the number of hurricanes per year. 336 divided by 55. That's easy. Find the probability that a randomly selected year there are exactly 8 hurricanes, assuming a Poisson distribution, if you can. And we're going to have to check out the requirements for that before we decide to do that. All right, find the P of 8, where P of x is probability of x. A 55-year period, 1960, 336. In this 55-year period, there were actually 5 years with 8 Atlantic hurricanes. How does this actual result compare with the probability found in B? Does the Poisson distribution appear to be a good model in this case? All right, mu, number of hurricanes divided by years. That's going to be 6.1 hurricanes per year on average. So mu equals 6.1. Perfect. And the probability of x hurricanes in a year is as follows. X equals 8, mu equals 6.1, E equals that, and you can just put that into Excel, put that into our calculators, and we should be able to get it. Plug it all in, you get 0.107. So exactly 8 hurricanes in a year is just 0.107 is the probability of that. Pretty low, but not extremely low. it's not less than 5%, so it's can happen. Probability 0.8 is the likelihood of getting 8 Atlantic hurricanes in 1 year. In 55 years, expected number of years with 8 Atlantic hurricanes is going to be 55 times 0.107 or 5.9 years. The expected number of years with 8 hurricanes is 5.9, which is reasonably close to 5. Actually about 0.9 off, but we'll take that. And so in this case, Poisson model appears to work. I don't know how to say quite well, but it does work. Now, this is actually, I said when I was closing up the last section, I was a little bit off on that statement. The Poisson distribution is not just an extreme of a binomial, but it can be used as approximation for an extreme for a binomial. So if n is greater than 100, so the number of events is greater than 100, and n times p is less than 10, the number of expected outcomes is less than 10, then we can approximate Poisson distribution with mu equals np. All right. Yeah, mu equals np. I'll pause for a second. And now we keep going. All right. In Maine, pick 4 game, you pay 50 cents to select a sequence of 4 digits such as 1, 3, 7, 7. If you play this game once every day, find the probability of winning at least once in a year with 365 days. This sounds really boring. But you're living in Maine, so I think everything is boring in that case. Is there exciting stuff in Maine? Anyone from Maine? Shoot me an email. Tell me some exciting stuff in Maine. And if you tell me the exciting thing in Maine is the Maine pick 4, I will be disappointed. All right. So n is equal to 365. The probability of winning is 1 out of 10,000. Because we got 10 times 10 times 10 times 10 for each of the 4 digits. It can be anywhere from 0000 to 9999. So 1 of 10,000. So n times p is going to give us a pretty low number. So p, n 365. N times p is 0.037. That is less than 10. So we can definitely use Poisson distribution. All right. Mu to the x, e to the minus mu, x factorial, 0 factorial. So the chance of you never winning at all is a 0.9642. So about a 96.42% chance that you won't win after playing for a year. That is not fun. All right. 1 minus that gives you the 0.0358 chance that you will win. So that's less than 5%. That makes it extraordinary for you to win. Probably not going to win. But if you do, you win a moose, maybe? I don't know what they give away in Maine. But, well, I guess that's the end of the chapter. All right. Thank you. That was a pretty quick one, too. And you got to see my face. I wonder if I should keep doing that. Maybe. I'll see. Let's see what the reactions are. Some people may say, just keep the lectures. Some people may say, keep the face. Some people may, have other ideas. Not care. I don't know. Here we go. If I can get the stupid thing to pause.